Hello everyone, this is Ketish here. In this video, I'm going to go through question number 6 from the AQA 2022 Combined Science Physics Paper 1 Higher Tier. Question number 6 is on the atomic model. A smoke detector contains a source of alpha radiation in a plastic case. A source of beta radiation in a smoke detector would be more hazardous than a source of alpha radiation. Explain why. Now, alpha radiation has the least penetrative power, so it's not going to come out of the plastic case. But if you have a beta source, that can penetrate plastic as well as paper, and it has a slightly bigger range than alpha. But the main reason here is that it would be able to penetrate the plastic case, which means it can irradiate the people who are walking past it. So answer: beta radiation is more penetrating than alpha radiation. So beta radiation would irradiate people passing near the smoke detector or the alarm. Question 6.2. Actinium is one source of alpha radiation. An actinium nucleus emits an alpha particle and turns into a francium nucleus. This can be represented as the following nuclear equation. So what you're seeing here is a nuclear equation. So that's the atomic mass, and this is the proton number. Remember, alpha particle is a helium nucleus. Helium nucleus has a mass of 4 because it has 2 protons and 2 neutrons, and the proton number is 2. So if I write those number 4 and 2 there, the mass number should add up. So 223 plus 4 for A, 223 plus 4 should give you 227, and the proton number Z is 87 plus 2. That should give you 89. Now while we are here, it'll be good to make a little bit of note. So what happens here in this question? They're asking what happens if it gives out a alpha particle. So I'm going to give you a little bit of note what happens if it does emit a beta emission. So remember, the atomic number -4 should be this value. So here, if it was giving out a beta emission, beta, the electron doesn't have a mass, so it will be the exact same number. So if I use the examples from above, let me make this slightly smaller so it's in view. Right, so I can use the same equation. That'll be 223, 223, Z plus 1, so this will be 224. No, sorry, that was a mistake. That should be 87. That will be 87. If that's 87, this should be 86. 87 minus 1 should be 86. All right, let's move on to the next part of the question. We could actually add this as well, isn't it? 223, 223, 88, that'll be 88. So in total, that should be 87 here. 87 should be the answer. Question 6.3. A teacher wanted to find out whether nuclear radiation is emitted from a source. The teacher placed different barriers between the source and a detector. So let's draw that slightly. So let's say that's the surface of the table, and that's my detector with a D, and that's my source, an S, and you're putting the barriers in between. Okay. So you've got paper, aluminium, and lead, which you're going to place in between. And you're going to work out what the reading is after 30 seconds. The teacher recorded the count for 30 seconds after each barrier was put in place. So without anything, the count rate was 985, which means it could have alpha, beta, or gamma without anything. Once you put the paper in, paper stops alpha. Aluminium would actually absorb the beta, and lead would absorb the gamma. So once you put the paper in, what you're left with is 149 counts for 30 seconds, which could only be either beta or gamma. Now, once you place the aluminium, that should stop the beta as well, which means there's 0. So there's no gamma. Explain what nuclear radiation was emitted by the source. How do you write this question? Answer, sorry. Some of the radiation was stopped by paper. So the source emits alpha radiation. It went from 985 to 149. And since some radiation passes through paper but is stopped by aluminium, so the source emits beta radiation, but does not emit gamma since no radiation is detected past the aluminium. That would be the 4 marks for this question. Next part, question 6.4. Figure 11 shows how the activity of 4 different radioactive isotopes A, B, C, and D changes over time. So we have the activities in becquerel here for these 4 isotopes. Question they're asking is, write the isotopes A, B, C, and D in order of increasing stability. Now, increasing stability means that it has a very long half-life. So whatever you write here for the most stable should have the least reactivity or the longest half-life. So let's work out the half-lives for this. How do you work out the half-life? Well, the half-life is the time it takes for the activity to reduce by 50%. So for A, starts at 400. How long did it take for its activity to reach 200? That would be somewhere there. So that's nearly, so if I write it on there, it's nearly 17 and a half, about 17 years. And for B, it starts at 250. Half of that is 125. 125 should be somewhere there. So that's there. So that is about 11.5 years. 11.5 years. C is going from 100 to less than 50. So it's going to be greater than 20 years for C. And D is gone from 150. Half of that is 75, which is here, and it's only taken it. Let's see, half of that. That's about 6.5. Yes. So D has the shortest half-life first. then B, then A, then C. So oops, all right. D, B, and A, C. The explanation was a substance with a longer half-life has more stable nuclei, so answers are in order of increasing half-life. That brings us to the end of the question and the end of the paper. Thank you for watching. I will see you in the next video.